All right, I wanted to record a really short video to go through some hints on the homework. We ended class and really didn't get a chance to talk about some of this. And I thought it prudent to just sort of go through some of the pitfalls that you might experience on the next assignment. So I want to focus primarily on the structural analysis side of things. Now, what you were told in the problem is that the beam is not experiencing any dead load beyond the self weight of the beam, which was a W24 by 68. So that means that the self weight is 0.068 kips per foot. But the beam does have two live loads. And what's more critical with this problem, and this applies to all the loads, is that it's not a simply supported beam, it's a cantilevered beam. Okay, and the nice thing about this analysis or this example and what's going to make your life easier than it could be is that for all of the loads, regardless if we're talking about the distributed load due to the self weight or the concentrated loads, either the 16 kips or the 10 kips, we're going to find some things that are universally true. One of the things that we're going to find true is that max shear and moment occur here, okay, at the support, okay. And that might not be the case if you had a simply supported beam, let's say, and a uniformly distributed load. Yeah, the maximum moment's going to occur at midspan. But if I had a point load and it wasn't at midspan, that might be kind of difficult. And we might talk later on about how you would address that in a design setting. But for the purposes of this problem, we don't have to worry about that. Long story short, if you did have a scenario like that, you just have to, maybe plot it in Excel, superimpose your moment diagrams, and go with the max. But that's not the issue here. All we need to recognize is that max shear and moment occur there, and max delta occurs here. So the maximum shear and moment occur at the support, the maximum deflection occurs at the end. So all you have to do is compute each of the components and add them up accordingly. So for example, for the dead load, we have the shear is just going to be, whatever this is, and the moment's going to be whatever this is. So W, D, L, and MD is going to be WL squared, WDL squared over 2. And the reason it's not WL squared over 8 is because it's not a simply supported beam. This is a cantilevered beam. So because the boundary conditions are different, the moment diagram is going to look different. This is what our moment diagram looks like for a cantilevered beam with a distributed load. It doesn't, look like this. So I know that artwork is horrible. Maybe I should do a little better job. It doesn't look, it doesn't look like that, where this was WL squared over 8. That's not the same story here. So because of that, those formulas aren't going to work. Now, what I was saying at the very end of class is there are these two loads here, this 16 kips and this 10 kips. If you try and say, okay, the beam is 18 foot long, that's 26 kips, so 26 over 18, and just turn that into a distributed load, that is wrong. It's going to result in a different moment and a different deflection. And since there is a deflection limit on this problem, you are not going to get the right answer. So you're going to have to handle each of these separately. So what I'll do is, it doesn't really matter. Maybe I'll do this one first and this one second, because that one's going to be easier. That first one's going to be easier. Is if I look at load number 1, that's going to be a concentrated load at any free end. That's going to be this one. So maybe I'll move this down here. And so in this problem, I've got PL is 10 kips, according to that a parameter that was given, and I've got that the length is 18 kips, and so from there I can say that the shear, we'll call it shear 1, is PL. The live load, or the live load moment for number 1, is PL times L, and the deflection due to 1 is what it is right here, PL L cubed over 3EI. Don't forget your conversion factor, your 1728. For number 2, however, so for number 2, when we look at this one, we have a little bit of a different scenario. We have this, and we have that. This is 16 kips, and this dimension is 12 feet, and this dimension is 6 feet. So go to here, okay? So in this situation, P is, we'll call it PL2, is 16 kips. L is 18 feet. I put kips over here. That was a mistake. This is feet. Sorry about that. I can see the comments now on the YouTube. Why do you need to fix that? Okay, but notice right here we've got this B parameter right here, and that B is the distance from the support to the load, and B is going to be 12 feet. And so now from these I can say, okay, VL2 is PL2. I should put ones in front of all these over here as well. ML2 is in this case P times B. And you know, looking at these formulas, like for example with the moment, it's really not that complicated. It's just force times moment arm, force times moment arm. So 16 times 12 and 10 times 18. It's just the moment. But the deflection, it's a little gnarly. It's this formula right here. P B squared over 6EI times 3L minus B. So you know you gotta chug all that out. And so then your live load shear is going to be VL1 plus VL2. Your live load moment is going to be ML1 plus ML2. And then your live load deflection is going to be delta L1 plus delta L2. You got to go through and stagger it out. So make sure that you know you're handling the algebra. If you try and turn this into a distributed load, you won't get the same answer. The answer, in fact, will probably be unconservative. Because, for example, worst case scenario for deflection is to lump that load all the way at the end. And by turning it into a distributed load, you'd be spreading it out. And that'd be incorrect, and it would be an unconservative estimate. So just make sure that you're, dotting your I's and crossing your T's on your analysis. Hopefully this helps, and I will see you all on Wednesday.